Hey everybody, today we're going to talk about moments of a measure and the still-cheese transform. To begin, let's define the moments of a function. The nth moment of a function r of x is defined to be the integral over the real line of x to the n times r of x dx. Notice, if we know all the moments of a function r of x, then we know how to integrate any polynomial times r of x. This is because if I start out with a linear combination of monomials, so some polynomial, which is the sum from k equals 0 to n of alpha sub k x to the k, then the integral of p of x, that polynomial, with respect to r of x, is going to be the sum of the integrals of those monomials, and can be therefore written as a linear combination of those moments. In particular, if I know the moments of a function, I can define the inner product on polynomials as we were doing before, and get a sequence of orthogonal polynomials for the function itself. What this means on the downside is if I have a sequence of orthogonal polynomials for some function, I know only so much that I'll be able to recover the information of the moments of that function. So that leads to sort of an interesting problem of under what conditions can we recover a function from some sequence of moments, and moreover, when is that function that we recover unique? One of the things we're really observing here is that in order to define our inner product, we didn't really need a function r of x of all so much as a sequence of moments. And this leads to the definition of what some sources will call a moment functional. So starting out with a sequence of values, m sub n as n goes from 0 to infinity, the moment functional is the function going from the collection of polynomials with real coefficients to the real numbers, defined by sending a polynomial sum from k equals 0 to n alpha sub k x to the k to the sum from k equals 0 to n of alpha k times m sub k. What we're observing from above is that in the case that these moments are that this sequence of values are the moments of some function, then it stands that the value of the moment functional on some sort of polynomial is exactly the integral of that polynomial times r of x dx. So definitely from a certain point of view, we could establish the whole theory of orthogonal polynomials just using these moment functionals. However, we'd lose a little bit doing so because the way that we defined these in the first place was we were thinking about ways of measuring the differences of functions on intervals and things like that. I think a lot of that good intuition is lost when we jump just straight to this moment sequence kind of setting. Furthermore, for the functions are the orthogonal polynomials that people use most commonly, there are unique functions which are defining their orthogonality relations, and so it sort of stands to reason to allow this level of generality to sort of sit in the background rather than putting it in the forefront. Even better, for a lot of for some very mild constraints on the sequence of moments that we choose, there is going to be a unique function r of x with those moments, or there at least exists a function, unique or not, with those moments. So we're really not losing anything in terms of generality when we're defining things intuitively in terms of integrals. But of course, this does lead to some interesting questions. For example, can two different functions have the same moments? And two, how can we recover a function from its moment data? Starting out with the first question, consider the function defined by sine of 2 pi of log of x divided by x times e to the minus 1/2 log of x squared. This is a sine function times what's typically called the log normal distribution. Let's calculate what the moments of this function are. I'm defining this function, by the way, only on values of x between 0 and infinity, since, of course, natural log of x has a little bit of an issue otherwise. So the moments of f of x are integrals from 0 to infinity of x to the n times f of x dx, which we can write down as integral from 0 to infinity of sine of 2 pi log of x times x to the n minus 1 times e to the minus log of x squared dx. This integral looks a little bit daunting, but if we do a simple change of variables, taking t to be natural log of x, so that dt is equal to 1 over x dx. This integral then becomes an integral from minus infinity to infinity of sine of 2 pi t times e to the nt times e to the minus 1/2 t squared dt. Now to evaluate this further, I'm going to go ahead and bring in and combine the e to the nt and the e to the minus 1/2 t squared by completing the square, rewriting this as sine of 2 pi t times e to the negative 1/2 the quantity t minus n squared dt. Now if I do another change of variables, and I use the fact that sine is 2 pi periodic, I can rewrite this integral as e to the negative 1/2 n squared times the integral from minus infinity to infinity of sine of 2 pi u times e to the negative 1/2 u squared du. And that integral here is going to be 0 just because of the fact that the function that we're integrating on the inside is odd. So what we've found is that all of the moments of this function are 0. So that really blows up uniqueness for us, because if I take any function g and I add f to it, those are going to be two different functions with the same moments. So clearly, we're not going to have uniqueness for the moments, for this problem, this moment problem, what's often called the steel cheese moment problem of recovering a function from its moments. However, under certain conditions, we will have uniqueness. The condition for uniqueness that is most often used is called Karleman's condition. And Karleman's condition says that if I start out with a function supported on some interval ab, whose moments are m0, m1, m2, etc., then we have three cases, depending on whether the interval in question is infinite both directions, semi-infinite, so it only goes to infinity in one direction, which we'll just take to be the positive part of the real axis, or the case where it's finite. And by virtue of just affine change of coordinates, we can assume that the cases break down in the following three ways. The first case, we can take the interval to be -1 to 1. And in this case, the moments uniquely define the function itself. Case 2, in this case, we're going to take the interval to be going from 0 to infinity. And in this case, what we require is that the sum from n equals 1 to infinity of those moments to the power of -1 over 2n, if this sum diverges, then the function is unique. And finally, in case 3, in this case, the interval is the whole real axis. And what we need is the sum from n equals 1 to infinity of all the even moments to be equal to infinity. And that implies that the unique function, there's a unique function with those moments. So the condition we're looking for is kind of a condition that the moments are growing fast enough. And that's a pretty thorough answer to that first question. The second question we were thinking about was, okay, suppose I have some moments. How can I piece together a function with those moments? And the idea for this is to rely on various integral transforms of the measure itself and how they relate to momenta. One particularly useful transform for this is the Steele-Cheese transform. The Steele-Cheese transform of a function supported on an interval AB is an integral from a to b of that function divided by z minus x. And here z is allowed to be any complex number away from the interval in question. So in particular, it could be a real number outside that interval too. And this defines a complex valued function, which we'll denote by S sub r of z as the Steele-Cheese transform of r. Now the Steele-Cheese transform is very closely related to the moments, and we can see this by doing a series expansion for the quantity 1 over z minus x. I can start by writing 1 over z minus x as 1 over z times 1 over 1 minus x over z, and we know a nice series expansion for the latter, so this is the same thing as the sum, and n equals 0 to infinity, of x to the n over z to the n plus 1. And if I put that into the Steele-Cheese transform definition, we can see that the Steele-Cheese transform is exactly equal to the integral from a over b of the sum from n equals 0 to infinity of x to the n over z to the n plus 1 times that function r of x dx. And assuming the function r of x is suitably nice, we can swap the order of the integral and the summation. And rewrite this as the sum from 1 over z to the n plus 1 times the integral from a to b of x to the n times r of x dx. And of course we recognize that as our moments. So this is a series, the sum from n equals 0 to infinity of the nth moment of our function r divided by z to the n plus 1. So our punchline here is that when our moments are suitably nice, so that sequence that we're seeing over there, that series over there that we're seeing makes sense and is absolutely convergent on a significant enough subset of the complex plane, then we can use the moments to get the Steele-Cheese transform. And once we have the Steele-Cheese transform, there's a process for taking that and recovering the original measure, assuming some continuity of function, assuming some continuity of the function on the interval at support. In particular, you can use a little bit of complex analysis to prove that r of x is the limit as epsilon goes to 0 from the right of the Steele-Cheese measure of x minus I times epsilon minus the Steele-Cheese measure evaluated x plus I epsilon divided by 2 pi I. To end the day, let's do an example. Suppose I have some function, r of x, whose moments are pi times 2 to the minus 2k times 2k choose k when n is equal to 2k, and 0 when n is equal to 2k plus 1. So in particular, all the odd moments are 0. Then using our equation from above, we can reconstruct the Steele-Cheese transform of the function r as the sum k equals 0 to infinity of pi times 2 to the minus 2k times 2k choose k divided by z to the 2k plus 1. And we can simplify this out by pulling a factor of pi over z and rewriting this as the sum from k equals 0 to infinity of 2k choose k times 2z to the minus 2k. Now if you stare at this for a long while, you'll see that this is going to involve the Taylor series of the square root of 1 over the square root of 1 minus 4x. In particular, if I recall here, that the square root 1 over the square root of 1 minus 4x is equal to the sum from k equals 0 to infinity of 2k choose k times x to the k. So with that in mind, I can rewrite my sum as pi over z times 1 over the square root of 1 minus z squared. 1 minus 1 over z squared, which of course simplifies to pi divided by the square root of z squared minus 1. Now as a complex valued function, this is a function which is defined on the whole complex plane, except for we have to cut out a little sliver here going from -1 to 1. And if I cut out that strip in between, cutting that out there, this is going to be a nice, well-defined holomorphic function on the entire complex plane outside of this little blue strip. And the values of the measure here are of x. At any particular x value, x, are obtained by taking the limit of the difference as I approach this point x going from this way or going from this way. And outside of that blue interval, I am nice and continuous, so that difference is always going to be 0. So what we're seeing from this picture is actually r of x is going to be 0 whenever x is outside the interval -1 to 1, so whenever x has magnitude greater than 1, and of course this is for real valued x. The interesting bits happen when x is between -1 and 1. And there we're looking at the difference as I approach some particular x value from above versus from below. So we're never actually evaluating it on that blue strip. So in order to recover r, we can take the limit using that equation above as epsilon goes to 0 of pi divided the square root of x minus epsilon times I squared minus 1 minus pi divided by the square root of x plus epsilon times I squared minus 1, all divided by 2 pi I. Now obviously the pi's cancel out, and the interesting thing here is that the way that the function actually changes from up here to down here is by a minus sign. So this whole thing up top here is really giving me the limit as epsilon goes to 0 of 2 times this quantity. So it's really just, and there's a divided by 2, so I can write it just as 1 over the square root of x minus epsilon times I squared minus 1, all divided by I. And as epsilon goes to 0 there, we can see that we're getting 1 over the square root of x squared minus 1, all divided by I. And I can remember that I is really just the square root of -1, so this is just all becoming 1 over the square root of 1 minus x squared. So this is for values of x less than 1. So what we've actually recovered here is that r of x was actually the Chebyshev weight, 1 over the square root of 1 minus x squared, and 0 for x greater than 1. And that's a good place to stop for today, so I'll see you guys next time.